Welcome to today's live stream, everyone. Today we have Nick Murzin and Amir Sabri talking about some kind of PiMachine.
Yeah, exactly. So some kind of PiMachine. We're gonna. So I've prepared some notebooks. I prepared it. Was writing a lot of code recently about related to this abstract machine and string diagrams, and so I kind of have a lot to show and just to discuss. We have Amir here, who is the author of this paper, which is mostly inspired me. Hold on, let me open up. Yeah, inspired me to write this booklet and to experiment with it a little bit. It's about interpreting string diagrams computationally. So usually there's like a typed lambda calculus, which only allows you to have closed categories and things like that without any U-turns and uh, ability to backtrack your computation. But this is like semantical language that allows you to have a actual abstract machine that runs your computation backwards and also do some garbage collecting. And we're gonna without me discussing what it actually is, it's just easier to show some code because I actually implemented this. Amir already had, and his co-authors already had an implementation of that language in Agda, which is like a nice uh, programming language with a very powerful type system, right? So because Wolfram language doesn't have a type system, so it was kind of hard to get all the inference checks right and actually construct correct terms. But you basically, with enough perseverance and debugging and all that, you can actually implement everything right, and it's going to work. And without, yeah.
Can you do like a symbolic? Can you just implement types in Wolfram language if you wanted to, like as a abstract?
Yeah, you probably you can do. It's like you can make some kind of special package for type theory and try to annotate and hint all of your expressions with types. It's a I'm already aware that a lot of developers within Wolfram Research are doing implementing some kind of type system with all different projects. So maybe it's time to actually abstract it out, make the common ground for all the type implementations with this ecosystem that we have, right? So in a way, this is just another way of doing types, right? So I've made a Packlet. I just updated it with some updates, right? So it has all the relevant symbols related to types, terms, and everything that we're gonna show. But so you can always install it from this repository and play around with yourself, right? But without further ado, we can just see what this actual machine contains and what it's all about, right? First of all, we just discuss what's the syntax. So it's abstract machine, right? So it's similar to lambda terms.
Can we start with the motivation? I always find before we go like too technical.
Well, motivation, yeah, I can talk about motivation. My particular motivation was I was looking into, I guess I can show you the paper was which was my original Rosetta Stone motivation. I think I already told you about last stream that we were discussing. Remember we discussing the string diagrams in general, right? And I bring back mentioned this paper by John Bias, right, about this Rosetta Stone between physics and computation, and also topology and logic. But mainly these two fields, physics and computation, are the motivation here. And in there, you basically use category language as your common ground, your Rosetta Stone, to describe processes in physics, which is your quantum theory or quantum computation, just your in finite dimensional cases, just quantum gates, state vectors, measurement, all that, and you have a computation. And there's just some basic description of the computation as a typed lambda calculus that you can also build some string diagrams, which is basically your diagrammatic language for some special categories. But there's no complete translation because you have much more richer categories for the quantum theories. You can have like a reverse dagger, you can inverse your processes, it's all reversible, you can have wires going backwards, right? You can basically you can have weird loops which are not obvious how to implement in for just computation in general, right? Especially like make it more rigorous. And so this paper by Amir is basically tries to do that by implementing some special types, right? So you have So let's just see what is all about. So you have this syntax, right? So what the first thing you have to have in your theory, in your syntactic theory for this machine is just types, right? So types are just objects in your category, right? And in quantum case, again, for motivation, that would be some like complex number, some kind of field. That's your type, right? And you can build products and sums out of those fields and make bigger objects in the same category. Here you have types, and you can also make some pairs, which corresponds to the product type, right? In the which also has a kind of interpretation as a multiplication in some particular sense. So if you make a product of two types, you get a new type, which is like formatted like this, which is like a pair. So this is like a corresponding value of that pair. Some summation type has an interpretation as a choice. So if you programmed in some functional language with strong types, like maybe Haskell, right? They have lists, tuples. Those are like elements of the product type, because you can just have multiple terms of that type. And the sum type is just like in Haskell it's called either. It's like a choice. You either have left or right. So you can have a choice of two types. So you can either inject your term, that's why it's called injection, either as a first choice or as a second choice, right? So it's just so you basically you have two terms of this sum type. You either choose first or the second one, or you can generalize it so that you don't have just the binary operators. You can have more summed so that you assume it's flat in some sense, right? That doesn't have to be that. And you have like special types, like a unit type, which is just a singleton type, which only has a single inhabitant, right? As just in our in Wolfram language implementation, just called one, right? It's just a term, but you have to make it a term. So this is just a single term of type one. So that's how I formatted basically all the terms which are not functions or not labeled. They always have these frames around them. So that's how I implemented them. So in a way, the way to construct this TT term, I haven't named it this way. I just named it, I have this pi1. You can call it like this or something, right? You just have, which only also formats as one, but it getting framed when you actually construct a valid term. So you can highlight that and see that it's typed one. So the pi unit type is the type, right? It's formatted as this double stack identity, and the term itself is formatted like this so that you can distinguish them. So basically, you have types which correspond to these things. We're gonna go to this negative and fractional weird types a bit later, but the basic part of the machine is just this unit, zeros, plus, and product types, which basically you already have them in the lambda calculus. I believe you can construct the more sensible part of the computation with those. If you're interested, you can have like pairs of functions. Oh yeah, we also have a function type. This is a little bit different, Amir, from the paper, because I implemented my terms and types basically. But let's look at the programs. So I have a list of combinators, there's built-in base combinators and some experimental one that I'll be already trying to implement. So we have a bunch of combinators which are functions. So a combinator is just a name of the function. For example, you have combinator identity, right? This is just formatted like this, and if you hover over it, it highlights that this has type from a blank to a blank. And blank is the pattern, so it's like a polymorphic type, which can be for all a. So it's just a function that goes from some type to some other type to the same type, right? And it also has some particular semantical meaning. So it's like just an identity function. Or for something different, for example, there's a time swap, which is like a swap function, which is if you have a product, which is a pair, you basically just swap around those. And that's where the diagrams come in handy. I think I can even maybe try to make a diagram of it if it works. Yeah. So I implemented some basic functionality so that they can turn those terms into diagrams, right? So this is like a swap diagram, which means there are two types coming in and they're just getting swapped. So that's
So
the
diagram for the identity, would it just be A to A?
Yeah, this would just a single wire. identity, like this. Right. So this is like shorthands that you can import by running this. This isn't so it's basically just a shortcut for extracting the named combinator. Instead of writing PiCombinator identity, and you can import this one. This context has a bunch of shortcuts like this, like ID, false, or maybe swaps and all that. Right? They return combinators.
And then why combinator? Why not just call it a function or something? Like, is there something?
Oh, I'm just following the paper language, right? So they were calling them combinators, but you can totally call them functions or programs.
Is it connected to lambda calculus in some deeper way that's why it's called a combinator, or not necessarily?
The difference is functions have free variables. Combinators are
Yeah.
they have no free variables. They're functions with no free variables.
Okay, that makes sense. Cool.
Makes sense, yeah. So now here you don't have any free variables, so it makes sense to call them much stricter version of the function, the combinator. Yeah. So what else we have? So we have a function types, right, which is just this annotated with arrows. So and the combinators are exactly as I said, are just terms of this type, right? So here it's like a separate line for describing program type, but this is just another type, and we have the terms for constructing values of these types and also the function types, which are some combinators. Here are some examples of the combinators. Actually, like this eta plus, I think I have it here, just called eta plus. It has this type, right? You can ask for type. So basically a function from 0 to some negative type plus positive type. So what are negative and positive types, I guess we're gonna discuss later, or maybe now, if you want to. But I guess another thing I should mention is how to actually run some programs with it, right? So in the IMU paper, there's like this notion of state, of the state of your evaluation, which is just contains 3 things, or depends how you count, maybe 5. It contains a combinator itself that you want to run. For example, I have some built-in large combinators like this. Like this is just a big composition of large amount of base combinators. Like you have this etas, identities, some associators, and swaps and all that, right? So you can compose all of these base combinators in some large combinator, which is going to be a program, right? It can have a type. In this case, type is just from A to A, right? You can look at the diagram for that thing. That's not going to be interesting, but I guess you can, because it's not the way I draw the diagrams are a little bit tricky, because I guess we can discuss what can actually those diagrams correspond to in case how do I distinguish summation and the product. So those are basically 2 different monoidal structures that you can have in this group, in this language, right? So we already discussed what products are, what sums are, which is like a choice. But in the string diagrams, it's very tricky to mix them together, right? So the one challenge to actually implement it is to have some diagrammatic rendering that works for both of them simultaneously, right? So that's a little bit tricky. So here, what I've basically done is that my summation types, like for example, this wire of 0 plus A is always going to be a single wire. And I'm not going to split it, and it kind of makes sense because it corresponds to a choice. You either have this one or this one. That's what summation is. But as soon as you have, let me, like for example, you've seen already swap, the product version of the swap. That's going to be rendered as a single as a multiple wires. So that's why, so if you have a product type, you can actually make 2 wires that running in parallel. So that's why we interpret product types and the product in general as a parallel computation, right? So it's not a choice. So it makes sense never to decompose your summation into multiple wires, even though you can do it. Like here, this dotted frame indicates exactly that. As soon as you have like a choice of 2 combinators, this is what here, if you look at this combinator again, you have this summation of eta and identity, right? So that's what this box is here representing. So it's a plus of those two. So it's like a summation if you have a choice, right? So that's why you can kind of frame it around, even though the input type is of some type, and the output type is also of some type. You can kind of inside of it still decompose it, but you have to bring them back together so that you never show. So those wires are not really a product types. They're not representing like parallel computation, right? They're and you can, if you have only the sum types and only the product types, you can basically draw the diagrams of the same thing. So maybe in the paper they have some examples. No, I don't remember. Some better drawn diagrams of those zigzags.
And what's the idea of the zigzag? Is it just to make a interesting pattern, or does it serve some?
Yeah, zigzag is just one base example. I think it's where it was. Well, I like this. So the zigzag corresponds to the diagram of this kind, right? So here it's zigzagging. You kind of introduce this U-turns into a computation, but if you actually interpret it as just as a running loop, this string diagram can be pulled apart into just an identity, right? You just because it's just a wire, right? So semantically, this should be identical to the identity. So that's the point. So we have just a single wire, but you introduced this special kind of U-turns, and you have to semantically also have a way to interpret them, and so that in the end, this program should be the same as running the identity or doing nothing.
So is the U-turn the result of the specific combination that you've put together here of these terms, or is it, I mean, like, is it by construction? And can you have U-turns constructed in different ways, or does it have to be this specific construction here to make a U-turn?
It is a special construction. It's a combinator, right? It's this U-turn is introduced by a special eta combinator. So it's a eta plus combinator that has the type that we already showed, right? Which has this type from 0 to minus a and a. So in a way, you interpret this backwards running wire as a negative type, and the forward moving wire as a positive type. So in a way, you created from 0, from nothing, two types of an opposite sign, right? So if you have a way to assign some cardinality to each of the types, that's where you have to be creative and somehow assign negative cardinality to a negative type so that it
That's pretty
preserves.
crazy. So it's like, sorry, I'm like trying to follow this. So it's kind of like arithmetic over types, over the type system itself.
Yes. You can have.
Can I give an example?
Please, yes.
So that's a zigzag example. So when I try to explain it to like informally, so think of the top wire as you holding some money, and the top right is somebody you want to pay that money to. Okay, so on one interpretation, the money flows and the person gets paid. But if I look at it by slices, vertical slices, so, and I'm going to start from the right. So from the right, the first slice, the person gets their money. So they gets the money. And then out of nothing, a debt is created. And so basically, like money, like I create from nothing, I create a positive flow and negative flow. So maybe this is when I swipe my credit card, the money's created over there, and then automatically a negative kind of charge is sent to the bank.
So in the quantum case, that's like a positron.
So there is that interpretation that people have been trying to say that this is a creation and annihilation of, electron positron or whatever, like kind of like an antiparticle from the vacuum. So that's the interpretation people give. I'm not going there because, I mean, this is a speculative interpretation, but it has that intuition, yes. Is out of nothing you create what you want, and you create a debt, and eventually the debt will be paid somewhere.
It doesn't have to be. It can just stay that way.
Well, no, I mean, in a closed system, it will be, because this is there's conservation of energy, conservation of information, conservation of everything. So in a closed system, it will be somewhere. But you don't have to pay it yourself. Somebody else can pay it in the closed system. If the system is open, of course, it can lie around until somebody, pays it at some point.
Yeah.
That's
There's like, there's some. Okay, go
sorry.
ahead.
No, just when you talked about closed systems, so the way you create these PiMachines, are they by default deterministic or not?
So this is all deterministic at this point, yes. So this is not quantum yet. I mean, we were going to quantum, but this is the core. That's before you go to quantum, this is the core.
Yeah.
So it's still classical, reversible. It has all of the machinery that you need before going to quantum.
Yeah, exactly. And about that interpretation as some IOU, your debt creation. There's a so like if you notice these pluses here, so in a way those creation is actually a creation of choice between negative and positive. So it's not like you're creating both at the same time, right? So if you actually interpret those antiparticles and particles or debt creation, it makes more sense to actually go to the multiplicative part of the same zigzag diagram, right? I don't know, Amir, whether you have a somewhere similar story, but about this type of diagram where there's a plus, so you have a choice creation.
Yeah. So this is the again. I have two paths. Let's say in a computation, I have a choice. I can give you A or B. Okay. I don't know what you want, so I'm going to give you A. If you decide you don't want A, or A doesn't fit your constraints or whatever, you come back to me with negative A, and then I choose the other branch.
Yeah, so it's backtracking. In other words, you just did some backtracking.
So
when the
if
constraints are not-
if you know the interpretation of classical logic using continuations, if I don't know if you know that's kind of what is happening. Is if you want to do proof by contradiction in and you want to give it a computation interpretation, that's the trick that is used. Is I would like to do A or not A in a classical logic system, but I don't have classical logic. I have constructive logic and continuations. So I initially say not A, and not A is not a thing. It's A arrow 0, right? Not A is a contradiction. It's given A, I get a contradiction. So I give you the not A part. If you're happy, you're happy. If you're not happy, you have to use, if you start using the not A because you're not happy with it or something, and you supply an A, it gets into a contradiction, which is the 0, which comes back.
Yeah.
And then the 0 comes back, and I say, oh, okay, I'll give you the other branch. So it's a way to kind of like make a choice, and I make the cheap choice right now, the very easy choice. And then if you don't like it, you have to come back to me, and I'll give you the other choice.
Yeah,
It's quite elegant, actually. Yeah, that makes sense.
you actually discuss. Yeah, this is basically this additive zigzag. If you don't actually split those wires and draw those loops as though there's some creation at the same time of the same choices, but actually treat it as a choice. That's the actual zigzag. Maybe if you follow all the wires here, maybe it makes more sense, but I doubt it. but we can discuss some continuation things because we started, like I mentioned, the states, right? The states is basically this kind of formatted as this tuple of combinators, some value, and some k is the continuation. So in a way, you can interpret continuation as this in some way of inversing your combinator, which allowing it to go backwards, right? Unrolling it, it's like a whole. That's how you actually construct here. It's like this. I have a special type called continuation, which is basically the same as function type. You just you use it differently. So it's a continuation type is basically almost like a function, but you treat it as a hole. You have an actual hole that should be filled with the function of this type, right? And that's how you, like, for example, interpret this square over here. So if you have a continuation, which is this third thing in this tuple, which is in your state, you interpret these holes as a placeholder for a function, right? So an actual continuation contains the type of this hole. I wonder whether it can also be interpreted as some kind of derivative of the function, because they also are holes in the terms, right? So maybe
yeah, that we've thought about, but we haven't formalized it.
Yeah, it's another complicated thing to think about, right? It's like trying to interpret it as a derivative, because you have arbitrary algebra of your types. So you have sums, products, and negative types, which are also like backtracking, going backwards, or also fraction types that we haven't discussed yet. So we can take some negative, some fractions, but if you allow it also to take some derivatives, you can do some like crazy stuff with types. All right, but so the continuations. Well, it's a bit tricky. It's technical. I'm not sure. It's like there's just I'm just showed the example of this zigzag. So in the way you actually run some program, for example, this zigzag program, for example, you can give it some term like false. False is just a Boolean term, the actual type, because there is no Boolean type in the machine. So Boolean is just a shorthand for 1 plus 1, because it's a choice between either false or true. So you can represent it as a choice between two unit types, right? You use either left, you interpret it as a true, and either right, you interpret it as a false. So basically false is just some particular choice. It's a first in that, basically first choice in that sum type, right? So it's a bit tricky. So that's basically one term. So that's how we can construct booleans. And zigzag has a type from A to A, so it can take arbitrary type. In this case, just boolean. So you can first, in order to run, you can construct this state. So I basically format it almost exactly as this state in the paper, in a more general sense with this directionality. So in a way, you can also assign in which direction the state is running, either forward or backwards. And then you just follow your writing rules. So you have all of those reduction rules, which is like rule number 1, 2, 3. There's like the whole list of rules how to run this machine given some particular state. You pattern match on it, and then use some rule in order for your from left state to go to the right state. So that's basically how any of these machines work, from lambda calculus when you do machine reduction, or to hypergraph rewriting. You just rewrite stuff. In this case, you just have some very specific list of rules. Like, for example, the first rule is just apply base combinator. So you know the semantics of all those base combinators, like identity swaps, association, when you just move parentheses around, right? You just apply it, and you switch this angle brackets to square brackets, and you interpret those angle brackets as you basically kind of your state, either it's in entry state or in the return state. So in a way, when you apply your base combinators, you always move from the entry to the return state. In a way, you return your computation. So in a way, this kind of terminates, but I don't want to say terminates. It just changes its kind to the return state. So it's ready to return. And when it's ready to return, it means that basically you now have to use continuation. So that's where the role of the combinator changes to the role for the continuation, when your state changes this kind from the entry to the return type. So it's basically when your combinator finished, like here you basically applied your combinator to the value and produced some new value. Now, because the state is in the return state, now you have to apply the continuation and fill the hole by this new combinator and change the state around. So in a way, you now follow other reduction rules that expect some return states, right? And maybe even turn them back around again. So we can follow some example rules. I don't know, maybe pick some at random and try to understand what's actually happening.
Is
If you
there a
want.
diagram for this one?
For which it's a
Or is-
reduction, not really a diagram. There's nothing to grammatically interpret here. It's just like composition. Like for example, take like this is just application of base combinators, nothing important. This is just the identity. It could be actually written as the first one. I don't know why it's the separate one. Amir is not here, so maybe he knows. But for example, if you have a composition, this semicolon means write composition. Run combinator one first, then the second one. And what does it mean as a reduction rule here? It basically create a hole, right, in the continuation. You're not actually running this anything here, right? Because you only know how to run your base combinators as a first rule. But here, if you have composition of two combinators, what you do is basically create a hole in your continuation, and then just focus on the first part of it, so that as soon as you run this first one using the first rule, right, you apply it if it was a base combinator, and you actually change the value, and it switches your state from the entry to the return state. Now you can actually start filling holes in your continuation, like here. You immediately can evaluate rule number 7. Right? Because you created this hole and you run your first combinator from here using the first rule. And now you again go into the entry state, but now you're focusing on the second combinator, right? So now you can run the second combinator because you already applied the first one to this value, and you can continue. So this is how you can interpret the whole evaluation of the state using just reduction rules. So you're just moving around combinators from left to right, modifying your continuations, creating holes in there. Also, all of this reduction rules semantically meaningful. Right.
Okay, and then the dot K means now that you've applied that continuation rule to the state. And the
Dot means it's just like a special composition of continuations. So you can interpret it as if you have a continuation which is called frame. I know. What do you know? Why is it called frame? Is it like a standard term?
Yeah, it's the stack frame. Yeah, I mean they're like a
because it's like a stack.
yeah. Yeah, sorry, I have somebody, a worker here, so that's why I interrupted. I'm sorry.
No problem. Yeah. So basically, if you have this, it's like a combination, like a special composition of continuations, which means if you have this black dot, if you fill the hole in this one, then the result of this you should use to fill the hole in this one. So that's kind of, you compose them like this, because this continuation assumes that there's a hole somewhere in there, right? And this is just all the rules show you how out of some base building blocks you move those holes around from left to right, and we can actually trace it around. So here's your initial state, right? You can create it, and then I have a function called eval trace. You can just eval this, and it's gonna just produce a bunch of states. Well, first of all, we just eval it once, not once, but up to termination. So essentially, you turn this angle brackets to square brackets. It means just it's returned. And as soon as you have this return state with empty continuation, you're basically finished. There's no further reduction rules that can be applied. If you go through all the rules, you're not gonna find a rule that can run on this empty continuation thing. It always runs on the frame here. For example, here, it always expects some kind of frame here. So no rule can be applied. But if you trace it, it's gonna be, we can actually see that there's like a lot of steps were involved, and we can look into some particular ones. For example, like the first ones over here, they were unwrapping this composition, because zigzag just contains the semicolon, which is just like one combinator after another, right? It's just a composition, and putting one by one into continuation. See, it's like, for example, first it put this one to the right and creating a hole on the left, right? Then you can put this one to the second frame and making a hole here, and so on, until you reach the base combinator here, right? Now this one we know how to apply. There's a rule for this particular base combinator that knows how to create basically a choice. Now you introduce a zero. So this unit introduction combinator basically introduces a zero because you basically can add zero to any type, right? So that's just a base combinator that introduces a zero. So now you can turn this term that we started with, which is just a false term, and make it a second choice, where the first choice is the zero. So basically, the why you can introduce a zero, making it as a sum, because you can always choose the term that you already started it. Basically, because you're not choosing the zero, you're choosing the term that you started it. So in a way, that's how zero introduction works. You can't choose the zero itself, but you choose the term that you started. So that's the unit introduction. So that's why this number 2 superscript means is basically the second choice in this pair, in this sum, which is the Boolean, right? And now we're in the return state, right? And when we're in the return state, that means we have to feed our holes in the continuation, right? So now we move this combinator over here again and pop from the stack a new combinator out of the continuation. And now it's again in the entry state, and we use other reduction rules, right? Now we use something that knows how to interpret summation, right? But for example, it first considers the second one, so it now it applies identity. Here the identity was applied. You pop the stack again. Now you apply this one, and so on. Basically, you go forward. It's like there's a lot of number of states that actually is required to run over this zigzag combinator, which is well, so that it ends up in the same term as we started it. Right. So I don't know. What do you have any questions now? But I can show another example. While trying to type it out, you can think of an example. Trying to remember how to make it. Right. For example, this was the additive zigzag. So that's exactly this one from the paper where you interpret every juxtaposition of wires as a choice, right? But you can also make the version of this zigzag where you just juxtapose those wires as a product. So now they're actually multiple values at the same type, not the choice, right? But the difference is, so that's the way you can construct the zigzag. So there are two versions. You just but you see that there is like almost identical, but this is using the sum types, but this using the same, but the product versions of those, like swapping the product and the association, also the product version of it. The moving, depending what brackets you're moving around, either in the summation or the multiplication. But the only difference is that this U-turn, like a creation of the pair, actually requires you to feed it with what term you will feed it. That's why, for example, that in the beginning when there was like we discussing syntax, this fractional type was a bit weird, odd one out. It's not really 1 over some type, but it's actually 1 over some value. All right, so it's like a dependent type. So actually, in order to create an inverse type like this, you needed to come up with some value, like a false or 1, not another type, right? And that's why the unit, not the unit, the eta, the unit combinator that creates something from nothing, the multiplicative version of this U-turn, right, which creates something from 1 instead of 0 now, has to also be fed with some term. In this case, I also feed it true, false, and we can feed it a true. So there are like, for example, if you want the zigzag for Boolean type, you can make 2 versions of those, depending on what inverse type of which term you're creating, either from true or false. So you can have 2 versions of combinators. And this one, actually, if you turn it into a diagram, hopefully it works. Or maybe I broke it. No. Hold on, maybe I have it. it should look like this. if I wouldn't, if I didn't broke it, I don't know why it doesn't work. Let me maybe. What did I do? Mm,
Or cache some terms or something. Local state.
Let me quit my kernel just in case. Hopefully, just it's because of the I'm juggling with those dependencies between diagrams and this much PiMachine. There's not good dependency.
That's a
handling.
cool. That's a handy little thing. So when you type in quit, that kills all of the variable. It kills the whole state of the notebook or what?
It just restarts the kernel. Yes.
Oh, that's handy. Okay, thanks.
Okay, I fixed it. So that's basically how we can construct the multiplicative version of the zigzag. The one thing I haven't implemented is like this should be like some kind of can try to rotate it like this grid, and I can rotate it to the right, so it looks similar, right? So if you interpret this one as a U-turn, it's just I'm making it very explicit that I'm not creating it from nothing. I'm creating it from a single unit. So I can also remove it. Just would have some problems later. But you can. This is the U-turn multiplicative version, and this is another one, the co-unit that annihilates pair and anti-pair, or particle and antiparticle. So that's what you should interpret as particles and antiparticles, because they actually created at the same time. And the computational interpretation for the inverse type, the one that has this negative direction, is not something that goes backwards in type and have some backtracking interpretation, but actually as a garbage collection or deallocation. So that's what Amir's papers claims, and comes up with this interpretation as you should interpret this in fractional types, the inverse type, as deallocating some value, right? So if you think you have created, so you can create a value, but you always have to basically make some kind of promise to also deallocate it later. So that's what your inverse type is. It's not like the choice that you like some inverse type which doesn't contradict with something later so that you have to backtrack it, but it actually just some promise to deallocate your value later, something like that, or garbage collected. So in a way you have this borrow checker built into this PiMachine, right? you borrowed, and you not borrowed it, but some kind of linear type handling.
Can you ensure that it's garbage collected? Like, is there some kind of surety or not necessarily?
Same thing. In a closed program, everything has to agree at the end. But the interesting thing is you don't have to garbage collect this value. You can use this value. You can create this value. So I created false. I can use the false. And I have a promise that some false value must be garbage collected in exchange for this one that I just used.
Interesting.
So I I allocated a value false, and I used it, and I created out of nowhere, basically. But now there's a debt that somebody has to garbage collect the false somewhere.
Yeah, but you can try to collect like a different value, and it's gonna fail. So
no,
right?
Oh yeah, no. If you garbage collect true, it doesn't work.
Yes.
But if you garbage collect false somewhere else, that's fine.
Yeah, that's fine. Yeah, I was like,
Yeah.
there's basically as soon as you have this garbage collection, you also can automatically have error handling, and you have throw exceptions. Exceptions in the unit language, because now because you'll try to handle garbage collect a different value. For example, this eta, that was the closing loop over here in the multiplicative versions. That's where the actual deallocation has to happen. But when your garbage collecting token, it's like doesn't match with the actual value, you have to throw an error. That's what this reduction rule corresponds to. So that's so basically your state. So now your evaluation of the program can also fail, not just terminate or loop around, but there's also fail state.
But doesn't that make it non-deterministic? Or is failed a valid end state? Like,
So this is
not
the
closed.
usual thing that you, in a well-typed program, this should never happen kind of thing. But, we
Okay,
kind
so
of,
you do a type checker beforehand to make sure that this wouldn't happen, something like that.
Yeah.
Okay.
And actually, if you're gonna speculate, I would write. I was thinking how to extend this language with a non-determinism, right? So kind of introduce some kind of distributions and all that. That's where basically you have to also interpret this failed garbage collection as because it's not deterministic anymore. So you have to try again. So in a way, it's not a throw of an exception so that you actually failed, but you actually try again your computation. You run it backwards, and because it's like there's some non-determinism, maybe the next time you will succeed, right? So in a
But
way,
the
your program
also-
can now loop around for a long time until it succeeds, right?
Or
And
never
that's why,
succeed. Is that
yeah,
possible?
and that's my hope to actually go to the quantum case. But I'm not sure I don't know whether I should go there.
Let's jump into it because I've only got 10 more minutes. So I'd love to think about that case as well.
Yeah, okay. I'm gonna show you the minimal example that I've been thinking about how to what this kind of program should support, what kind of type of computation this program should support in order to think of it as quantum, right? I know Amir has another paper about how to make the pi extended version to the quantum case when you have some kind of pair of those pi machines and one of them rotated, right? He has this paper called How to Bake a Quantum Pi, right?
Yeah.
And the
great.
idea was there to have some rotated version of the pi machine, and that's why you kind of the way you introduce angles and things like that. But I want kind of more basic approach, right? I want to explain it now. So whoever watches our stream maybe already knows about it. It's all revolves around phase space and quasi-stochastic maps, things like that. But maybe for a mere benefit, I'm gonna like go through it again and explain what kind of how to think of quantum computation, mostly classical, almost classical, right? Just basically move everything not classical into something else. So for example, if you have the basic example of a quantum computation, just apply an operator to a state, right? You can pick some random unitary and random pure state. So that's our minimal quantum computation, right? So we're gonna you obviously, because they form a string diagram, this compact category, you can move around those wires. So your unitary operation can be bent around. This is the same as above, right? So you can create these U-turns in quantum computation. You can make a circuit like this, which is basically, and it's going to be identical to the U itself, to the random unitary itself. Or you can do it like this. Another thing you can do, because there is a state operator correspondence, you can always interpret, kind of inject this operator into one of the U-turns, and now you can interpret this just as a state, right? Now it's not an operator but a state, but it's equivalent. So in a way, you can always make this correspondence. But another thing, what you can do as soon as you have states, you can always cast all of your states into a phase space where they just look like, if you know about phase space interpretation, formulation of the quantum theory or quantum computation, it's just the way to represent Hilbert spaces in a real dimensional space. You have to square your dimension. So if you started with a qubit where your amplitudes are just pair of amplitudes, right? You square it. Now you have a phase space representation of the same space, which is just 4 numbers, real numbers, and which is called basically a Wigner function. So a Wigner version of the quantum state. So in a way, you can think of any distribution, any quantum state as a quasi-distribution. And you can even go beyond that, and you can actually make it not a quasi-distribution, but an actual distribution. I'm not going to explain how to do it. It's related to positive operator valued measurement and things like that. In a way, you can basically cast your quantum state into probabilities or a special operator, which is complete. So in a way, you represent all of the information of the state as probabilities, right? It's all known in the quantum Bayesianism and POEM interpretation of quantum computing and so on. But in the framework that we have here, in the quantum framework, it's very convenient. We have just phase-space transform, and one of the bases that you can transform your states into and all your operators is this symmetric information incomplete one, which is basically make your arbitrary state is just into a list of probabilities. So they're not quasi-probabilities. You're always going to get positive numbers that sum up to 1. So that's just a way to interpret any state as a probability distribution, right? But the problem is that that's what you can do for the state. But when you did this weird correspondence with operator state duality, you kind of reverse the arrow. So there's some problems. So you actually have to take it into account. And the way you can do it, you can basically, in a more detailed way, you can also decompose your operator. Because in this basis, your operator is going to look like not distributions, but some quasi-distributions because of that reversing of the wire. But you can also decompose that into 2 pieces. So in a way, you can think of your original U operator as some combination of forward map, which is just a stochastic classical map, which is just you can think of it as a conditional probability table, right? Just a stochastic map forward, and some inverse of it. So this beta is also another stochastic map, but it's a reverse of it. So in a way, in this picture, for example, which is exactly equivalent to the above one, but now all the pieces are classical. The only non-classical thing is because you have to run this computation in reverse. So in a way, what is your stochastic map or conditional probability table in reverse? That's inference. So in a way, you have to infer the value, the initial value from the resulting value, right? And you can of your non-deterministic map, the stochastic map. So that's the only non-classical part, is to actually be able to run the inference within this computation. So you have a non-deterministic computation where you can just sample your random values. You can use your conditional probability tables to sample new values. But as soon as you hit this inference part, you have to do something weird. And it's going to be especially weird when you deal with correlated variables and things like that, because you have to perform this inference without distracting your correlations. That's where all the non-locality going to come into place. So that's why this kind of thing. Yeah.
This is fascinating, and I don't want to interrupt because I know. But after this, please send me this. You're saying this is all known, or you started known, but
Kind of known, but it's known, but it's like scattered around. It's very simple to.
I'd like to collaborate on this and work on this a little bit. This is fascinating.
Yeah, it's just not very well known, but it's known, and it's especially useful because it's in our Parklet we just have code that does this, so it's very convenient, right? So, yeah. So basically, that's the only place where non-quantumness comes into place. Yeah. So we have to know how to make this inference on a single value. So that's my original motivation. As soon as you have this Rosetta Stone that allows you to go interpret computation and quantum computation with just string diagrams, it makes sense as soon as you have a computation, this PiMachine, which is basically the way to run classical programs corresponding to the string diagrams and do this backtracking and garbage collection. Maybe you can, and because you have the explicit state with a single term at each slice of your circuit, right? Of each slice of your diagram, and where you're not dealing with probabilities, not dealing with amplitudes, you just have a single value living in the wire, right? And my motivation was basically would you extend this machine non-deterministically, right? Introduce some distributions so that you can, and then also come up with a semantic interpretation of these U-turns so that you can run it around all the computation so that in the end, the final value when the machine terminates or maybe not terminates, but closes into some kind of stationary distribution, so that the actual probability of the final value is the one that you get from the quantum computation, right? So basically, you should make your semantics such that it basically does the inference. So basically implements this inverse stochastic map somehow. So that, right? And I was kind of hoping that this inverse stochastic map can be implemented using more clearly by this just backtracking or garbage collecting or like some combination of those, so that you can just run around. Your state can just run around in your computation back and forth, so that in the end your value in your final state is the following the correct probability distribution, right? So that's the idea. So for example, James,
And
if you remember, like,
yeah,
yeah, if you remember, like maybe a couple of months ago, I was talking about those inhibitors. I was just running those simulation. Basically, I was trying to implement inference kind of in a similar way, but not rigorous enough, right? I was kind of like, if you think about this inference, I was just literally introducing some
inhibitor.
finite number of inhibitors, I was calling them, right? So that your computation can bounce
Has to
around,
go back, and forth.
bounce around those inhibitors, but without rigorous construction. Basically, I said, as soon as it bounces, it just restarts the thing, and you just decrement the number of inhibitors somehow.
Yeah, so these continuations can kind of like you can build it rigorously now.
Yeah, now I'm hoping like you can implement those. Well, there's some problem with those, but I was hoping you can do it. You can solve those problems if you actually make it rigorous. For example, one of the problems was the main problem was there's like not clear way to come up what would be the number of those inhibitors. So actually, because if you make it too low, you just have a little number of bounces. It's not going to be statistically significant. You're going to have like you basically made your very small number of inference steps or something. You haven't inferred properly your final value. But if you make it like, if you bounce it for more, somehow I implemented the same idea for Bell experiment, and somehow you could reproduce some super quantum correlations. So in a way you can,
oh God.
yeah, in a way you can exceed your quantum correlations if you bounce too much, right? So you have to like constrain it somehow in some meaningful way.
I need to jump off this stream, but yeah, I'm gonna watch the rest of it from here, on the recording.
Yeah. So for example, this diagram in the more in the process theoretic diagram ways, when you have the types and arrow directions also implemented. Like, because we're dealing with the phase space, we're basically dealing with pairs of Boolean values, right? Because now it's like for example, spin up and spin left, spin up, down, spin left, right. So we have two Boolean variables, so it's a phase space. That's why there are a pair of them. And now we have the direction, right? But because this goes backwards, it's still a stochastic map. So basically we have to somehow to come up with semantics of probability distribution when we can run this program so that it correctly implements the inference part. So that's
what happened to the 1/b situation?
Well, here I needed this because there's no like a direction of the arrow. It wasn't clear that it's inverse. But here I removed it because it's like goes backwards. But you can still think of it as, because this is here as an input. So we wrote an inverse map. It's just a label. you just have to keep in mind that that's inverse map over here. Inverse map because it's also
inversing the pair.
It's inversing not the pair. It's inversing your stochastic map. So if you use your conditional probability table to resample, for example, you have a 2x2 conditional probability table, like given where the input has some value of your coin, right? Or
yeah,
false.
like spin up and spin left.
Yeah,
That's
spin
like
up, spin
one
down.
pair of values.
Yeah. For example, 2x2 conditional probability table tells you the new probabilities of what to sample the new value, or true or false, right? If you follow that table, that's like applying the stochastic map. Just multiply. But here's the inverse. And the inverse one usually when you inverse the stochastic map, it's going to contain some negative probabilities in there. So that's why you can't really interpret it as some conditional probability table. You can't run it directly. And there's no interpretation of it running directly. You have to implement inference somehow, like make some Bayesian steps many times, or do some minimization or something like that. So you have to, in a way, pick into input distributions, not just the single value, because the stochastic map itself can be run once given a input value, right? You give an input value, you look at the column in your stochastic map, that's your new probabilities, you sample a new value from those, right? But when you have to do it in reverse, you actually have to know the distribution itself, and you can't determine it from the a single value sample alone. In a way, you have to pick into the distribution or run it multiple times to actually infer the original distribution, so you can faithfully output a value, right? As though you run this process in reverse. That's the problem. That's why the quantum interpretations have this classical problem, like classical
because of the negative probabilities.
Because of negative probabilities, but if you go further, those negative probabilities basically tell you that you have to infer it, and you have a problem with realism, because you can't explain everything with a single value, like with a point in the phase space, because you have to actually have multiple points, right? And in order to have multiple points, you have to run something multiple times, and if you had some correlations, you actually have to pick at the values somewhere in another place of your galaxy or whatever in your Bell experiment. That's where the non-locality comes from. You have to infer the probability of your correlated pair too, right? It's not enough to just look at the single value.
You're saying you have to like empirically decide, like deduce what the probabilities are by running like experiments on that diagram.
Like
choosing different values, input values.
Just try to come up with a single experiment. For example, if you have say you have a distribution like this, right?
Yeah.
And you have a simple stochastic map, something like given basically with the same value, like this. Let's call it S. Right? This is like your conditional probability table. If you run it forward, you get a new probability distribution. So in a way, the way you interpret it in the just forward moving computation, you just can resample it, right? If you just give me false or true, I just pick a column and sample from a corresponding column of this matrix, and I get the correct value with the correct probability that.
Wait, so you're saying if false is 2/3 of the time and true is 1/3 of the time, then for example, if you like,
then
S dot P is 4/9 is false, and 5/9 of the time is true.
Yeah, exactly. So it's like a new. So that's where we're running the stochastic map forward.
Mm-hmm.
So in a way, we just applied, and you can do it, and you can run it on a single value. You don't have to actually know this probability distribution in order to run it, right? If you give me false with this probability, I can just generate true or false from this probability distribution by following the column in this matrix, right? I just sample from the column and I get correctly the sample from this distribution. But if you want to reverse it, right, you of course linear algebraically you can do it by just inversing the S matrix here, and that's where you get the negative
probabilities in there.
Yeah. So this one you can't interpret as a conditional probability table, right? You have to know how to sample from this column, right?
Mm-hmm.
There's no way to sample from this column because it doesn't make sense.
Yeah, it can't
you have
be
to run your Bayesian map.
False -1 of the time and true 2 of the time.
Yeah.
Right.
Yeah.
Uh-huh.
So there's no deterministic way to no direct way of resampling to get the value corresponding, even though you can run it, right? If you like call this Q, you can run it in reverse and recover the probabilities, but there's no way to recover those probabilities given a single value. And you can basically think of all the quantum weirdness of the quantum computation just living in this inverse maps, right? In the way to do the inference. And this here we just isolated it and also put it in the backwards moving wire, even though you can kind of slide it to anywhere, but here just in the correct place, maybe, in order to come up with the interpretation for it, so that you can maybe think of it as just bouncing around, garbage collecting tokens or whatever, so that it, yeah. So that's the hope. I don't know how to do it. I would really want to discuss like how to construct the basics of probability theory, even maybe before even all the quasi weirdness and negative probabilities, just the basic probability theory with those types. Even this is already tricky. It's like I scout the literature, and it's like there's nothing. But even though if you think about it, it's kind of even as soon as you have fractional types, and if you actually assign fractional cardinality to those types, that's your probability distribution, right? I don't know whether Amir you thought about it at any way. Can be about fractional types basically be your weighted choices. So as soon as you have some type of fractional types, that's your distribution, if the fractions sum up to identity. So in a way, as soon as you have a eta, your unit, instead of the additive version of it, instead of creating as just a choice of either minus a or a, you have a multiplicative version when you created fractional types instead that
Yes,
sum up.
I didn't think of those types as probability, but I did think about something similar. I mean, I didn't know any of that, but so I had like some intuition of something like that, where uh, there is like a forward and backward negotiation, if you want, to try to get an agreement between the forward flow and the backward. So the forward flow offers some kind of values, maybe guesses them and offers them, and the backwards flow says yes or no. So you can offer half a value, half a false, 1/3 of a true, whatever. And then on the way back, it says, no, I don't want this. I would like 2/3 of that. And
Yeah.
so maybe this is how, I mean, maybe this is matches your kind of your formalism here, where the inference is more like a negotiation back and forth.
Yeah, it is. It's like if you, I'm pretty sure you're familiar with transactional interpretation,
Exactly.
right?
That's exactly where I mean I got this idea is I was trying to formalize the transaction interpretation.
Yeah. I kind of agree with that. It's like you can think of these transactional events that are so that you can have like emission, absorption,
Yeah.
transaction between events. But those are the problem with those transaction events. Okay, that happen out of time, right?
Yeah, no, but I mean in nature, out of time, we write it in time. That's fine. I mean, we can simulate the process. I mean, our backwards interpretation here will take time.
Yeah.
The physics interpretation claims that the backwards happens actually backwards in time, but that's a different story.
Yeah, it is. Like my hope is that with all this, to have the computational interpretation of the physics is basically, I don't know, do you familiar like with Wolfram physics framework and how we like think about events in there as a computational updates in your state and things like that?
So in fact, I have a collaboration that we just started trying to formalize the transaction interpretation. And this is kind of like where I was. So this is like so amazing that this is what you're talking about. And you formalized like a huge chunk in a very elegant way.
Yeah, and actually playing around with some ways to make some stochastic things. So I don't know, it's like, for example, I'm not particularly sure what it's like. Like one thing you can do, right? For example, it takes a seed, so it's deterministic. So in a way, where you can like, first thing you can do is just create, interpret your distribution like this, right? It's just a choice. You create from 1 or maybe from 0, I'm not even sure, right? You can just create a choice. That's what your sum type is. You either the first, second, third, or fourth, right? That's what your distribution can be. You can feed it with some probability distributions that kind of what combinators you can introduce, right? But I don't like it because it's like false fails this cardinality checks again, right? When you interpret this as like 4, you kind of want your combinators to preserve cardinality
Yes, because
in
we
order to make
that as entropy.
yeah, otherwise it's not reversible.
Yeah.
Even though it's like we want some non-deterministic but reversible. So this kind of having this distribution that creates this choice that have cardinality 4 actually implemented some cardinality thing. So, for example, if you have this type, this cardinality is 4,
Yes.
right? But it's like 4 here, 1 here, so it's not good. So that's why I was thinking maybe if we want to create something from 1, we need to have fractional choices, and where the cardinality is actually also fractional. So
Well,
that's basically one.
I think that I mean it's a good idea. I don't know all the details, but so I'm definitely going to follow up with you because this is fascinating. Very excited about this.
By the way, yeah, thanks, Samir. I'm also looking forward to collaborate, finish this. I want to figure it out. It's like a year of the quantum. We need to figure out quantum this year somehow.
So you want to apply this PiMachine to quantum computation?
But not to apply it. We want to derive the quantum computation, having this computational semantics.
So you want to
Using
compile quantum like circuitry into
in a
this
way,
language.
yes. In a way, yeah. Given you give me Hilbert space gates, and I pop out a pi combinator that I can just run around and with all the semantics with types, backtracking, and garbage collecting, and it somehow it reproduces the quantum computation. That's the goal, I think.
Oh, that's fascinating.
Yeah. But this like thing about negative and fractional type is also fascinating on its own.
Right. So
It's kind of
negative type was like you wanted to get rid of something, and fractional type was a way you wanted to deallocate it from memory or something.
negative type is like a backtracking. So it's like you hit the constraint, like Amir explained. You had a choice of negative and it like failed your constraint, and you have to backtrack back and generate a new choice, right? But the fractional type is like garbage collecting. It's like you have to allocate it something with the promise to deallocate it somewhere else. Something like yeah. And here maybe you can use the same types in order to also represent distributions and also stochastic maps, obviously, and maybe quasi-stochastic, so that your inference also works naturally. Hopefully somehow.
Quasi-stochastic. I mean, is there an avenue for looking at multi-way computation in all of this?
The multi-way is just I think yes. It's like in this evaluation, in that trace that I showed you, like with a bunch of states. As soon as you on its own, it was deterministic in this implementation. But as soon as you implement non-determinism, so that your computation can take multiple branches, you can do some multi-way formulation of that too, right? Yeah. But now it's like I'm mostly interested in not even in the negative types. I think negative types are less mysterious than the fractional types. It's like there's some notion of a negative cardinality. There's some theory of negative sets with negative cardinality. There's like this exists. So there's some formalization, but about fractional types, there's basically nothing. It's like in the Amir paper, it's interpreted as some kind of garbage collection. There's a earlier paper
Right.
that interprets them as some functions from linear type to unit types, but it doesn't like hold up with the cardinality argument. It's like for example, in one paper, like inverse type, like 1 over a, it basically was a to unit, right? But functional types, cardinality wise, are interpreted as 1 in the power of a. So in a way, this is like has the same cardinality as a itself, and not 1 over a, right? But like if you kind of
Depending on what
but
A
if
is
you
as a object, as a set, what is A?
it's a type. It's a type.
type.
So they all have Yeah. So this is like a function type. This is the fractional type. But you can also write fractional types, function types. If you want to compute the cardinality of the function type, you usually have like the right-hand side raised to the power of the left-hand side, right? So in a way, if this is have cardinality 1 and this cardinality a, the overall cardinality of the function is 1 over a. So it's still 1, right? Not 1 over a. But I was kind of wondering why, if you have a make sense, if we do have sense for negative cardinality types, why can't we just define our fractional types as a functions from negative instead? So it's like, I think it makes more sense to interpret fractional types as functions from negative type to 1 or to some b, right? Like this would be b to the minus a, right? Or 1 to the ba, something like that.
There's that B over A. I don't know. I'm just thinking out loud. I mean,
Well,
does the inverse, does this fractional type pair with the multiplication operator to like give the unit again?
Yes. So the one categorical interpretation of fractional things, there is groupoid cardinality. So this is again in category theory and in homotopy type theory, and they have this groupoid cardinality. So if you have a groupoid is like essentially a group with multiple units, if you want, like something like that, intuitively. If you have essentially a bunch, like a set, and then a bunch of equivalences between points in the set, if you're going to count the number of elements in the set, you should divide by the number of equivalences. So let me put it like something very simple. I have 4 points, and I have an edge between the first 2 points and edge between the second 2 points.
Mhm.
So I should count the set as having 2 elements, not 4, because the first 2 are indistinguishable, they're equivalent, and the next 2 are equivalent.
Right.
So you divide by the number of equivalences. So now if I take a set with 1 point...
Or do you count the number of equivalent classes? Equivalency classes.
And now if I have a point with like 5 equivalency classes, then this is 1/5. So it's equal to itself in 5 different ways. It has 5 symmetries of some kind, and
Okay.
there's like 5 different ways of equating it to each other, this object. So this is how this is how I've learned about fractional cardinality. And I've tried to kind of connect it to this work, and I could never kind of get the computational interpretation working. But in terms of categorical semantics and categorical kind of development, this thing exists.
Yeah. Do you know whether this kind of
I
correspondence
like the
exists?
minus. I never thought of this minus, even though I should have. So, and 1 over a is like minus a to 1. That's interesting. So that's also that. If that works, that'll be very interesting.
Yeah.
So there's definitely a lot of kind of cool manipulation on types that I think are the key to get quantum out of classical. I mean, that's what we're playing with here.
Yeah. I'll definitely keep thinking about it because I was only implemented this thing like with all the types and terms just maybe a couple of days ago. So I just was thinking of how to do the non-deterministic version of this and type semantics maybe for a couple of days, right? But but this distribution, I want to play around what can happen, what kind of semantics I can assign if I think of distribution and creating a choice of fractional types, and when the fractional types are indeed functions from some negative types to some other thing, right? For example, I can create 1 over 2 type as just a function from Boolean, right, to unit. Oh no, it's from It's from unit to Boolean. For minus unit. Yeah, I was already confused. So it's like, this is my fractional type that is a function that takes some value of the negative types and producing a Boolean. So that has like 1/2, 1/2 cardinality.
Yeah.
And you can even do, as soon as you have this kind of simple algebraic thing, maybe you can even do square roots, right? You can now have functions that have square roots as like high order functions or something.
Yeah. So there's also you've seen the 7 trees in one paper, you know that one?
Well, I've seen it mentioned.
Okay.
Yeah.
So if you write, okay, when you write a binary tree data type, essentially its t is equal to 1 plus t squared.
Yeah.
Because like either a leaf or a pair of trees. 1 plus t squared. Now treat this as a polynomial.
Yeah.
And solve for t. It's a square root of 3, blah, blah, whatever. Okay?
Yes.
Now, manipulate the polynomial, you can actually prove that t to the 7 is equal to t.
Yeah.
And so there must be an isomorphism between 7 trees and 1 tree.
Yeah.
And actually there is one. And
Yeah.
the type t is minus blah square root of 3 plus 2, whatever, like some. And so there is this idea that you can actually have arbitrary types. Algebraic, all kind of algebraic operations that you imagine on numbers can be used on types. You can build a type that's half square root of, this plus that minus that, whatever. And trying to interpret that is interpreted computationally as like a computational process is not easy. I mean, even that 7 trees in 1 is difficult because it also implies that t to the 6 is equal to 1. Which algebraically it is, but computation makes no sense.
Yeah.
So there's a lot of very interesting things there.
I know. Yeah. It's fascinating. So yeah, but now we have like some playground.
Yeah, I mean, so I'm gonna email you after this to kind of get. I want to get some kind of something to read about your what you said is obvious or kind of well known. I want to read about this, understand it, and then talk about the collaboration.
Okay. I'll send you some papers about like this POEM things and all that.
Yeah, that would be that. Yeah, thank you. That would be great. Yeah, thank you so much. Okay, thank you.
All right, great.
Yeah.
Nick, do you have anything more, or should we close on the live stream?
I guess any comments on the live stream? Any comments? No.
Memes is there. He says that B over A reminds him of the golden ratio.
B over what?
B over A.
Or how?
Willem, are you there? Do you have any questions? Comments? Okay.
All right. Okay.
Thank you, Omar.
Thank you so much. Thank you.
Thank you, Nick.
Thanks everyone.
Bye, guys.